Hello, good morning, good evening, good afternoon, everyone, wherever it might be. It is my great pleasure to begin a new academic year with our local postdoc, MANISH KUMAR, and he will tell us everything and more about factoriality and fullness of q-ARAKI-WOODS for Neumann algebras. MANISH, the floor is yours, the Zoom is yours, take it away.
Thank you, Kurt, for the introduction and for the invitation. So, this talk is about something called q-ARAKI-WOODS for Neumann algebras. And although this seminar is non-commutative geometry, probably you will not see geometry, but you will see non-commutative. So I hope something will be interesting for the audience. So this is joint work with Adam and Matthews and some ongoing work with Simon. So I will in the end talk about work with Simon on fullness results. So the plan.
Oh, wait, we might have to click on it, yes. Okay, try it now.
Yes, so here is the outline for the talk. So we will discuss three questions: factoriality, non-injectivity, and fullness questions of q-ARAKI-WOODS for Neumann algebras. This was introduced by Hiai in 2003, and some of these results are very recent, although the algebra itself was introduced quite long back. And I should emphasize here itself that these Neumann algebras are associated with three data. So we have three data here, a real Hilbert space, and we will mostly assume it to be separable. Some of the results will work probably in non-separable cases as well, but we will restrict to separable case. And UT will be a representation of orthogonal transformations on this real Hilbert space. And Q will be a number strictly between -1 and 1. So the plan is to give construction of these algebras, and then I will talk about the history behind some of the known results, especially on factoriality and fullness. And then I will talk about our contribution in this question.
So the fact that the Hilbert space defined over real numbers is essential here.
Not really.
Not really.
Yes. So I will tell you. It's just the data that we are starting. So everything will be in a complex. So all the algebras in Hilbert spaces ultimately will be over complex plane, but your initial data will be a real Hilbert space. That's all. But we will actually complexify the real Hilbert space. That's all we will need here. So
after complexification, all this Q parameter still be will be between -1.
Yeah, so the Q will always be
real.
fixed. Yes, this is real. Yes, I don't think it in general works for complex case, but in some cases it does. So there are some constructions, but not for this talk. I will not talk about them. So because I have enough time for the talk, I will start with the definition of fundamental algebras. So a fundamental algebra, as you all know, is a self-adjoint subalgebra of bounded operators, which satisfies this bicommutant relation. So the commutant of any subset of bounded operators is the collection of operators which commutes with everything in the set. And the algebra, fundamental algebra, is called a factor if the only commuting element in the algebra is the scalar multiple of the element. And broadly, factor can be divided into 5 types. Essentially, we have these 5 types. So IN will be IN is just n cross n matrices, or 1n. I infinity is bounded operators on an infinite dimensional Hilbert space. 2-1 factor is an infinite dimensional factor, but it is equipped with a normal faithful tracer state. So 2-1 factor is distinct from I infinity, and 2 infinity is a direct tensor product. So this here denotes the fundamental algebra tensor product. So these are So this is just a polynomial tensor product of a 2-1 factor and a 1 infinity factor. So it's a tensor product of this and a BH like this. So and if a polynomial algebra or if a factor does not fall into these 4 categories, then it is of type 3. So essentially, types are well, in general, if you see these notions in the books, you won't find it defined like this, but and this is a shortcut way of telling these things. Okay, so let's see an example of a 2-1 factor. So one natural example comes from group functions. So for us, group will be discrete and countable. For any element S in the group, we define these translation unitaries. This is coming from left representations or little L2, and they are defined by translating from by left translation of the inverse of S. And the group polynomial algebra is just the polynomial algebra generated by these left translation unitaries. These you can also think as a strong operator closure of the reduced group C star algebra, if you have to say. And here I have listed 3 properties, 3 results, because these are the results that I am more interested in, especially for this talk. So a group polynomial algebra is a factor precisely when the group is of infinite conjugation class, meaning that all non-identity element has infinite conjugacy. And once the group is ICC, then it is always a type 2-1 factor. And so a type 2-1 factor here comes always equipped with a normal faithful tracial state.
So can you remind me what ICC stands for?
So infinite conjugacy class. Yes. So if the precisely non-identity element has infinite conjugacies, and 2-1 factor meaning that there is a unique normal faithful tracial state, and the tracial state can be precisely given by this. So this delta is actually the function which is 0 everywhere except at identity E, and at E it is 1. So that's the meaning of delta E. And note that everywhere you will see the linearity of the inner product in the right variable. So this one X is coming in the right.
Is the trivial group ICC?
No, not by our definition.
So ICC should always be
Infinite.
infinite. Yes. Okay.
And the group is amenable. So amenable means that there exists a linear function, positive linear function on L infinity of G, which is left invariant. So it is one of the formulations of amenability of a group. So when the group is amenable, if and only if the group polynomial algebra is injective or amenable or approximately finite dimension. So these notions are equivalent because of the famous results of Allen cones. And I will describe you, I will tell you what injectivity is. Amenability, I will not tell you what they are, but I have just mentioned here because the group, that terms appear for the group. So amenability essentially uses derivations of fundamental or binary spaces. And approximate finite dimensional, as the name suggests, is that you can approximate your group polynomial algebra by finite dimensional subalgebras. So that is the meaning of AFD. And this you see, you must have seen in C star algebras in many other places. And here the approximations would be in von Neumann algebraic sense. So it's to take weak closure, strong closure of an increasing sequence of finite dimensional subalgebras.
Does the last point also hold for uncountable ICC group? Amenable.
Yes, I think this is true in general.
Okay. But I remember there's a open problem saying that if G is a locally compact group, it's not known that whether it's amenable is equivalent to LG being injective. In the uncountable, in a non-separable case. In a separable case,
but at least I think for discrete group it's true, but I'm not sure what it is.
Okay.
Wait, so what would be an example of an uncountable and amenable group? Sorry, no, this is trivial hardware, of course, yes.
Yeah.
So any a million loops.
Are copies of T product together.
Maybe, but
But
yeah,
do you regard R as discrete group or locally compact?
locally compact, I think it means.
Static assumption of discreteness here.
I think the non-trivial part is whether LG being injective implies G being amenable. If G is locally compact and non-separable.
I know what questions I have to ask. It's about second countability. So an example of an amenable group which is not second countable.
All the appealing ones. All the appealing ones, the compact ones,
Yeah, a billion ones are always.
or compact ones, elementary expectations of both. It can be very, very large.
Like with Tikhonov topology, right?
Yeah.
Okay, good.
Okay. So let's see the definition of injective phenomenal algebra. So a phenomenal algebra, a concrete realization in a Hilbert space H. It is called injective if there exists a bounded projection E, and the projection here simply means E square equal to E, and it is bounded by 1. So it is actually independent of your choice of representation, but you can start with a given representation of M on a Hilbert space.
So you don't assume it being somehow self-adjoint? It's a projection independent.
It's a projection, yeah. So you don't assume E to be. It actually ultimately is true that E becomes completely positive, but in the definition you don't have to. So here are some examples. So naturally, BH is itself an example. You can take E to be identity. Now, Cohn's proved that there is a unique separable injective to one factor, and that we are denoting it by R. So, in particular, by uniqueness, R is isomorphic to any group phenomenal algebra LG if G is an amenable countable ICC group. And in particular, you can take G to be say symmetric group on infinite symbols.
And then this projection is what? In example 2?
So, for example, if you take G to be amenable, then you have these states, and out of these states, you can actually define the projections. I can't precisely, you can actually, so you have a trace on your phenomenal algebra, you have these projections, and somehow you can compose and get this E. So we can actually give concrete.
How can you obtain this projection from this trace?
So you find a state on your BH, and well, how should I say? So basically, you are asking in this definition here, given amenable group, how it is injective. So
I don't remember if this result about equivalence between injectivity and amenability, and this approximately fine.
yeah, of course, in that way also.
Is this theorem effective?
You can bring it that way. For example, you can say approximately for an amenable group, you will get a sequence of positive definite functions with finite support. That is another formulation of an amenable group. And out of those finite positive definite functions, you can actually define completely positive map with finite rank. And that way you can approximate identity on the group phenomenal algebra by this finite rank completely positive maps. So that is another formulation of injectivity. So that way also you can immediately show.
Yes, so this is property of.
So these are all equivalent conditions of injectivity.
Yes, but how to use this property to get this projection from the trace?
Yes, you can get
You conjugate the left regular representation, the average over the invariant state. Something.
yeah. So I don't exactly remember the formula, but yes, you can
Formula.
use the.
Okay.
This is the easy.
Yeah,
Easy
thank
implication.
you very much.
The other side is quite difficult. Right?
So from other side also, if you have a projection, then getting a state actually is also easier. You can just restrict the to L infinity. Anyway, and the third example, I have listed it here, but I'm not going to give you precise construction or anything.
But these are not the same ALGEBRAS, right?
Yes, for the namesake, I have written it here. So these are classically constructed by these two mathematicians, ARAKI and Woods, and they constructed this something called infinite tensor product of finite type I. So these are examples of type 3, or well, the example also includes type 2-1 factors. So in particular, these examples among type 3 factors are examples of hyperfinite or injective factors. And although these names, the ARAKI and Woods name will appear in the upcoming slides, there are reasons why this name appears, because I will just comment on that why this name appears rather than going into the details of that. Okay, so as the name suggests, these are like a tensor product of matrix algebra, if I have to say, infinite tensor product.
What is unique about the factor R? Like for each particular Hilbert space, when you consider, like you can construct a von Neumann algebra inside B of H for each one, which is unique, or?
No, so of type 2-1, among type 2-1 injective factors, they're all isomorphic. So uniqueness means that there is just one injective 2-1 factor. So isomorphic as for Neumann algebra, not as like representation, not like unitary equivalence. But, yeah. And here are some non-examples of injective factors. So last slide said that when G, the group is non-amenable, then your group for Neumann algebra is non-injective. So in particular, the free group is non-amenable. So LFN is an example of non-injective factor. And this example is will be important for us, at least in the beginning, where I will give you the construction of these free Gaussian factors. So
Could you define Gaussian factor?
yes, so I am going to say that. So these two examples are what the topic of this talk. So I will actually explain these things. Yes. Okay. So let me just quickly go through the classical theory of commutative. Even if we will not be getting much into the details of these results, but just for the sake of having the notation set, I will just say a few words about them. So you start with a fundamental algebra with a normal faithful state phi. Although this result, the construction or any definition you have mentioned for very small class of like a small class of fundamental algebras. You can do it in general for say Bates and general Hilbert algebra. So, but for us, say let's say M is a fundamental algebra with a normal faithful state phi. L2M will be the GNS Hilbert space. There is just the completion of M with respect to this inner product here. And for each X in M, you denote the same element when you look it as vector in L2, then you denote it by X, just that is just notation. And now you define this operator S0. So these are subspaces. You think them as dense subspace of L2 of M. So S0 is defined as a linear operator on between dense subspaces of L2M, and S0 is defined like this. So it sends X hat to X star hat. Okay. So this is just on this is only defined on this dense subspace. Now it is a fact, you can check it, verify it, that S0 is actually a closable operator. So it's a pre-closed operator, meaning that if you consider this graph and take the closure, then the closure of the graph is actually graph of another operator. So they are of course as unbounded operator, and they are not linear, these are anti-linear operator. And because it is closable, you can close it. S is the closure of S0. And you can check that as unbounded operator, S inverse is equal to S. So if you think it is an unbounded operator, then S square is actually contained in identity. That is the meaning of this. Okay. Now we consider the modular operator, which is S star S. So even if S is empty-linear, this modular operator is actually linear because S star is also empty-linear. And this is S equal to J square root of delta is the polar decomposition. And because of this condition, you can check that this J satisfies this. You can also check it by uniqueness. That J is actually a unitary, anti-unitary if you have to say, in the sense that J square is identity and it is anti-linear. So here is the main big result of Tomita, which says that you can get the commutant of M. So M is here always represented on this L2 of M phi. So when M is represented on this L2, then you consider the commutant. This commutant is precisely given by J and J. So every element of the form Jx from M, Jxj will be in the commutant. And this is also a very nice result, which says that this delta, when you consider delta to IT by functional calculus, then these are unitary operators. And by conjugating with these unitaries of an element in M, we will land in M itself. So a priori, these operators are not in M, but still the conjugation is in M. So
just let me ask you a bunch of naive questions.
Yeah.
So one in Tomita's theorem, is there an easy part, like for instance, that everything of the form Jxj is in the commutant? Is it clear, or?
that should be the easy part. Yeah.
Yeah, that's the easy part. Difficult is to show that everything in the commutant is of that form, right?
Yeah.
Okay. And another one, when you look at this hat, this mapping X to X hat, that's injected, right? Or
Yes. So M, yeah, this is injected.
X.
Yes.
By faithfulness of phi.
By faithfulness of.
By the way, is there a version of this Tomita theory for non-faithful states?
Yes, there are.
Weights.
Even for non-faithful states there are. So, but yeah, I mean, you restrict it to the support and you work with the compression with respect to the support and many things work actually. Okay, and because of this result, you can define this group of automorphisms. So here X actually, so X here will belong to M, and these homomorphism sends element from X to X, and they define a group of one, say a group of automorphism. So they are called modular automorphism group. So these notations will be used in between somewhere, but you don't have to bother much about them if you didn't follow much. Okay. So let's now come to the main object of this talk. So we want to talk about these Araki-Woods factors. So I want to give you construction of this q-ARAKI-WOODS phenomenal algebras, and remember that it is associated with three data. There was a number q between -1 and 1, and this real space HR, and there was an orthogonal transformation UT. So my plan is to give you the construction step by step. So first I will give you the construction for the case when q equal to 0 and UT will be trivial. So UT will be identity for every. So which means that we will simply start with a real Hilbert space. Although for the sake of this slide, you don't have to explicitly assume it to be like this. You can start with any complex Hilbert space and do the construction. But for the next slide, we will see that HR is important. So you complexify the real Hilbert space, HR. You consider the nth tensor product for each n. And for n equal to 0, you set it to be complex. And omega will be, so this omega will always be a fixed unit vector that we call a vacuum vector. And then you take the tensor product. This is called Fock test, free Fock test. And on this Hilbert space, this free Fock space, we define these creation operators from left. So as the name suggests, from left, it creates a vector. So it sends n tensor Hilbert space to n plus 1 tensor Hilbert space. So on omega, on this omega that we have fixed, on this it sends xi omega to xi, and on n tensors like this, the LGI acts like this. So it just add this xi in the beginning of this
You call it Jai, this is Xi.
Psi, yes. Yeah, thanks.
And I'm confused, sorry. What do you gain by talking about the complexification of a real
Yes,
Hilbert space? Are you come?
Yes. So for the sake of this slide, this is really not important.
Okay,
Yes.
okay.
So
Then
these definitions, everything makes sense for any complex.
That's
Then
my
we
point
have this
exactly.
Anti-linear conjugation, not conjugation, it is idempotent.
Yes, so that is an important part. Yes, that is. So it is an easy exercise that when you define it like this, then you can extend it linearly to a bounded operator on the whole of Fock space Fh. And the formula for the adjoint can precisely be given like this. So on this vacuum vector omega, the adjoint acts like 0, and on n tensor, the adjoint sends an n tensor to n minus 1 tensor. So it kills the first element here, and it keeps the other minus 1 element. So that's how the adjoint acts. This is called inhalation operator. Okay. And here, out of this creation and inhalation operator, you define this free Gaussian phenomenon. So I sort of mentioned it. This was defined by Kulescu, I think way back in 80s. And these are defined. So this notation is just to show that okay, it is dependent on some initial data HR, and these are defined to be the phenomena that are generated by these self-adjoint elements by sum of creation and inhalation operators. And here is where the real part comes into play. So here you vary this operators only over the vector coming from the real part. Okay. And if you have varied it over whole complex part, then you will end up getting different phenomena. So that is a very important thing. Okay. And essentially, you didn't have to start with a real Hilbert space. You could have started with a complex Hilbert space. But what you had to do is that you had to fix, you could fix, say, an orthonormal basis. And then you vary this xi only over that orthonormal basis. And you will still end up getting the same phenomenon. So in that way, you don't have to start with a real Hilbert space. But again, that is same as a real Hilbert space, because then you take HR to be just a real span of your orthonormal basis.
But once you consider the non-trivial representations, HR will all still be important.
Yes, so there it will be important. So that's why once we come to the next other constructions, then this real part will be important. So that's why I have presented it in this way.
And an orthonormal basis would generate the same phenomenon.
Yes.
Sorry, what about commutation relations between L oxi and L oxi conjugate?
Yes. So I will answer your question in this slide.
Okay.
Yeah. So here I have listed 3 properties. So the vacuum vector that we had fixed, the vector state coming from these vacuum vectors, it defines normal, faithful, and the most important thing is tracial state. So this state here, where this dot denotes the variable, it is a normal, faithful tracial state. And this is a result which goes back to 80s, which says that if, well, the dimension at least 2 is not important, but what is important is that this free Gaussian phenomenon is isomorphic to the free group factor, where D is where D symbol is the dimension itself.
It can be infinite.
T can be infinite. Yeah, it can be actually, I think, non-separable.
Oh, okay.
Yeah, that is not important here.
Could you explain what is the source of the tracial property?
Why is it tracial?
Why is tracial?
Yes, this is important from this fact.
On this reality.
From this reality. So I can't give you exact calculation, but you can imagine that. And we will see that actually this traceability goes away once we have a bit of deformation in the inner product. That is an important one. Okay, so the moment we have this isomorphism, you can immediately conclude that it is a non-injective to one factor, because we have seen that the free group factors are non-injective to one factor.
The group is not amenable.
Yes. So these Gaussian polynomial algebra can be like all the properties of this polynomial algebra then can be immediately concluded from whatever you know about the free group factor. But the idea behind this construction was that Vasilescu wanted to understand the free group factor from different point of view. So you
Is
can,
that isomorphism very difficult to prove?
no, it's not. You can actually concretely give the formula.
Oh.
You can check their book. So this why Vasilescu constructed this, because by constructing this he created this whole field of free probability, and actually there was a lot of tools then available from free probability. Like you can use things from combinatorics or random matrix theory and use it to attack problems in fundamental algebra. So that was one of the great success of this construction.
Is there a relation between these D generators of FD and this
Yes, yes. So, yeah, for example, you can fix an orthogonal basis of this,
Yes.
the orthogonal basis.
Hmm.
And out of those orthogonal basis, you have these self-adjoint elements. And these self-adjoint elements are precisely the.
Okay, so for every psi I, let's say, from
Yes,
this orthogonal,
Yes.
okay,
You can,
you obtain a generator of FD.
yes.
Thank you.
Okay. So here is the relation that we were asking for. So these LIs in this case actually are isometries, right? I have written it here like 0 simply because I want to put Q here. And these are isometries with orthogonal ranges, orthogonal ranges. Okay, so they are precisely how you say generate Punj algebra or something. These are the left creation operators behind the image. And we actually want to understand the Q analog of this relation. So I want to give you the construction for operators which satisfy this relation.
But do you replace this free Fox space by some,
Yes.
let's say Q?
Yes, exactly.
Okay,
That's the construction that is behind this.
so they will be, say, Q anyons.
Exactly, yeah. Okay, yes.
Q equal to 1, it would be about
And it will be CCR algebra or something.
for Q equal to -1.
Yes, yes, exactly.
Kernels
Yes,
and-
yes, exactly.
Okay,
But for us, Q will also always be a
but it is strange that for this anyons, you allow only real Q between -1 and 1.
I will talk about why it may fail in general. So I will tell you in the next slide.
Okay,
By the way, this relation reminds me very much having Q presentation, quantum disk presentation of it, that is algebraic. Instead of with delta ij, you would write y minus q, this would be precisely a quantum disk relation.
So there was actually for quite long discussion open in 80s that, okay, can you find operators which satisfy this relation for general given? There were some suggestions and of course the question was that you have to find bonded operators and in such a way that it has a nice representation say on Fox spaces or kind of. So that was the question which was like solved in 91 by Bojik and Spiker. So that is the construction that I would like to give here. So this.
so I have a question, Piotr.
Yeah.
So do these Fox spaces play a role in the theory of quantum disk?
No,
No,
no, but I'm just wondering, when I look at this relation for Q equal 1, I know you exclude it, but then you have something which has no bounded representation.
Yes, yes. So in the case of CCR algebras, these left creation operators are not bounded.
Okay, so. Okay, thanks.
But you can still take the, say, you can use the functional calculus and you can still generate the fundamental. Okay, so here is, so we have now a fixed number between -1 and 1. We still have a complexification of a real Hilbert space. Again, for the sake of definition, you don't need H to be like this. Now we consider the algebraic tensor product and algebraic tensor product, and we define these linear operators, Pn. And this is defined like this. So we are defining it on a spanning dense subsets. So you define it on n tensors like this. So this sums over all permutations on n symbols. And this in of sigma denotes the number of inversions of the permutation. And it acts like, so permutations play here. So you permute the vectors like this. Okay. And if you have seen the definition for this anti-symmetric or symmetric Fock space, CCR or CR algebra, then you precisely get the same definition by putting Q equal to 1 or minus 1 in that sense. Okay, now Bojeikin and Spiker showed that this operator is strictly positive in this case. So in anti-symmetric or symmetric case, when you take Q equal to 1 or minus 1, it's not a strictly positive. So you have to actually quotient it by non-zero vectors. But here it is already a strictly positive, which means that this definition gives you an inner product. And in the case of Q minus 1, you take quotient by non-zero vectors and you get these anti-symmetric relations or inner product. And a priori they are not complete, so you then complete it with respect to this inner product. And this notation will be, so Q here will be for the completion with respect to this new inner product. And then as before, you have this Q Fock space. And again, we have a fixed vacuum vector again in this case. So now we have got a Q analog of our free Fock space. And then you can define these creation operators just like we had defined in the free Fock space. So it sends omega to the vector side and n vectors like these to n plus 1 tensors.
So here there's no Q here.
So in the definition here, there is no Q. Yes. So the definition for left creation operator precisely is like this.
But it's a joint, has it not? Yeah,
It's Q.
Yes. So now because the inner product has changed, it's not immediately like it's not so easy to show that okay, this definition actually extends the bounded operator. But that's precisely what Bojeikin and Spiker showed. That at least when Q equal to Q is between minus 1 and 1, and even for Q equal to minus 1, you can show that this extends to a bounded linear.
But not for Q equal 1.
Not for Q equal. Yes. Okay, and the precise formula for the adjoint can be given by this, and here Q appears. So now you will note that although this adjoint sends n tensors to n minus 1 tensor, this n minus 1 tensor, so this one is disappearing. That's what meaning of this hat is, and the adjoint is killing every single vector at one point in the simulation. So in the previous definition, adjoint was killing just first vector, if you remember, in the free Fock space. But here it kills every. And as I had mentioned earlier, these left creation and left inhalation operators satisfy this Q analog that I was mentioning. These operators are satisfying these relations.
So I wonder what is happening in this limit, Q equal 1 or minus 1, because if you speak about symmetrized or anti-symmetrized tensors, then putting tensoring with this psi in the front of this multiple tensor product is subject next to this anti-symmetrization or to symmetrization.
Right.
So it seems that in this case the definition of LQ is different from this fermionic and this bosonic cases.
Inner product, you mean?
Because you are not applying this Q symmetrization to this formula.
No, but if you put
so you are regarding this as a free tensor product. You are putting this psi at the beginning only.
yes.
And you are not applying this Q symmetrization. Because in this fermionic case, it's like exterior product with psi.
Right.
In this case of bosonic Fock space, you have this symmetric product.
Right.
But here we are putting only this side in the front of all this expression, but you are not applying this Q symmetrization, which is strange.
Yeah, so,
Because this construction doesn't fit to this family parameterized by Q with these limiting points minus Q and minus 1 and 1.
yeah, probably in the limiting it may not be available. Mhm.
So therefore, LQ is independent of Q because of the lack of this symmetrization, Q symmetrization.
Well, yeah, at least this definition you can say like that, but I mean, yeah, in the calculation, definitely Q plays rules. So, but in many of the applications,
Everything depends on this faithfulness of this symmetrization,
right, yes, and that is that
which is not true in this limiting case.
exactly. Yes, yes. Okay.
So maybe it's equivalent, yeah.
So we will see that actually when
Sorry, so maybe, could I continue
yeah.
my comment? So maybe because of this faithfulness
Mhm.
of this symmetrization or anti-symmetrization, you can symmetrize or Q-symmetrize,
Mhm.
but you can forget about this symmetrization by the fact that this projection is a strictly positive operator.
In many cases,
You can speak about the action on the tensor power, forgetting about this symmetrization.
in many cases you can, but I don't think you can always forget that. I don't know in what sense you mean, but this Q in many cases.
I'm trying to understand why you can avoid for Q between -1 and 1 this natural operation of Q symmetrization, because it's the obvious choice for the definition of this creation and annihilation operator.
Yes. Well, I'm not sure how to answer your question, but yeah.
Yes, it's right, but
Yeah.
but
Okay. So as before, we have this Q Fox space and acceleration operators here. So you can define, now we are naming it as Q Gaussian polynomial algebra. And the definition is precisely the way we had defined earlier. And again, real part plays a role here. So we are varying the vector only over the real part. And as before, again, although there is a deformation of the Hilbert space, the inner product, but the deformation is not happening at H level by Q. So the traciality still remains a fact. So this vacuum vector still induces a normal faithful tracial state on this phenomenon. Okay.
could you explain the motivation, this motivation for this Gaussian?
Name.
Yes. Why Gaussian?
So the free Gaussian term, I think, in free probability, the Gaussian is like the counterpart for the Gaussian, the classical Gaussian measure is the semicircular Wigner distribution, the semicircular distribution, and these operators actually these are self-adjoint operators, and if you calculate their distribution, then it is precisely semicircular distribution. So
how this is related to, for instance, Gaussian property of a random variable?
So in free probability, whatever in classical probability, Gaussian distribution plays a role. In free probability, it is played by this semicircular law. Semicircular law. And yes, so the name is like picked from the classical case, but in free probability, it's not exactly the Gaussian that plays a role, but it's counterpart that plays a role. And these operators actually has that property. The way
Is this semicircular law in the classical case equivalent to the Gaussian property of the random?
Not really, but it's like the law,
Property.
the distribution is given by 1 minus x square in the unit interval. So it's I don't know, it's not exactly uniform measures on 0 to 1.
I remember correctly, it's all about the central limit theorem. In classical case, central limit theorem says, okay, it goes to Gaussian,
Yes.
and the non-commutative counterpart to it is the semicircle.
Semicircle, exactly.
Okay,
Here,
Yes.
I don't remember what's this distribution called, but I don't think it was called Gaussian. But it's this.
it should be called. Am I?
Yeah, probably some, yeah. So the name was initially suggested by Voiculescu and it has remained, so, I mean, it's what is kept in the name, so that's what.
Okay, thank you.
Anyway, so here I have listed some properties of this Q Gaussian phenomenon. So we saw that the free Gaussian, meaning that for Q equal to 0, it was isomorphic to free group factor. So you immediately concluded that they are non-injective to one factor. But for Q non-zero, it was not so easy to prove that it is a factor or it is non-injective. So it took quite some time to prove it. So for example, in 97, these three authors, Bojeko, Kumar, and Spiker, they showed that when the dimension is infinite, then you have the Q Gaussian phenomenon as a factor. Then in 2004, Asniadi proved it for a large class of cases when the dimension is large, so large which depends on Q, then it is factor. And in 2005, Ricard completed this factoriality question. And then before Ricard, there was a result by Alexander Nu, who proved that they are non-injective. So far, these four properties so far says that, okay, this Q Gaussian phenomenon behave precisely like free Gaussian phenomenon. But, and in 2014, these two people actually showed that for when the dimension is infinite and Q is small in some sense, then they are actually isomorphic to the free Gaussian. So this 0 is here for Q equal to 0. So it means that in this case, they are all isomorphic to free group factor. So in some sense, they all behave like free group factor. But a very recent paper of Martin Kaspers shows that this is not the case when the dimension is infinite. So this Q non-zero thing is actually very different than, it could be different than Q equal to 0, in particular for this dimension being infinite.
I wonder if there's some analog of this free group inside of this gamma Q.
Analog of free group.
If you remember, there was an identification for this in this free case.
So you mean analog in the group case, like group phenomenon?
Yes.
I think that's not known in general. I am not sure, but
There's nothing like the formed kind of free group.
I think it's not known.
Is it known?
Okay.
I mean, it should be a very interesting question to ask whether it's the phonemic algebra or some quantum digital, which should be analog of the field. Yeah.
Very much open question.
Yeah.
All of you are invited to look into
Very
it.
interesting.
So it's these phenomenon algebras are still not very well
We
understood.
even have the candidate for the higher state.
So
Yeah.
okay, so we have seen two construction, Q phenomenal algebra, Q Gaussian, and so there this UP I mentioned in the beginning, the representation of one group of orthogonal representation. This was not playing any role, but now this will play the role. Now we may consider them to be non-true. But still, for the sake of simplicity, I will keep Q equal to 0. So that was the way it was initially defined. So I'm going to give you the construction in that way. So we still have a real Hilbert space and one parameter group of orthogonal transformations. Then you as before, do the complexification of this real Hilbert space. Now this UT, this can be extended linearly to as a unitary operator on this complexification edge. So now you get a one parameter group of unitary operators. Okay, and then you can ask a Stone to give such analytic generator A. So any one parameter group of unitary operators can be written like this. There is possibly unbounded positive invertible operator. So invertible as unbounded operator. Now, this A plays the role in a new inner product that we are going to define.
Wait a minute. A to the power IT or E to the power IT times A?
So you can take A to be E to the power
So-
A.
A should be in, if it's a generator, it should be in the exponent.
Yeah, it's like this one I read.
Not A raised to IT.
So you have equal to E to the
E,
power
yeah,
I,
yes.
like this,
Yes.
and take A equal to E to the power H.
So you call this a generator.
You can call it like that.
Okay.
But here H is
Usually the generator is the H.
yes. So here H is you can
Okay.
H is here a self-adjoint operator, but when you consider like this, then it is a positive.
But you're still calling it generator.
Yes.
Okay.
So using this A, we define an inner product, new inner product on H. And at first it may sound weird, but this is very natural. If you have gone through classical things, then you define the inner product like this. Now A inverse is an unbounded operator, but it is positive. So 1 plus A inverse is a bounded operator. And its inverse is a positive invertible operator. So this is a well-defined inner product. That's an important thing. And then with respect to this inner product, you take the completion, and this U denotes for the completion. So in the previously we had deformed the nth tensor product by Q, but here we are deforming this complexification itself. Okay, so that's an important thing. Okay. So we will see that this deformation actually takes away the traciality that we were considering earlier. So now we will have non-tracial states. So that is the motivation behind defining this. And this way it is defined. If you understand, if you go through the modular theory of this phenomenal algebra that I will be talking about, then this inner product is very natural from that aspect, and this A is very natural from.
So instead of a trace, you have some twisted trace.
We will have some state, but it won't be tracial. It will.
Yeah, but it will be twisted trace with some modular operator, which is conjugation by this.
No, there will not be any trace. That's the conclusion that we will see. So we actually land up in a type 3 phenomenal algebra world where there is no tracial state.
No, I'm talking about the twisted trace.
So I don't know what you mean.
The trace property, but the trace property for the price of conjugating by this operation.
I'm not sure what it means.
So the trace property is that apply to the product.
You commute it.
Apply to the product in the opposite order. Okay, twisted trace property is like apply to the product is equal to the same as applying to the product of in the opposite order, but one factor must be conjugate by some operator.
Yes, so it's like KMS.
Okay.
So that KMS conditions, it will be satisfied. Yes.
So it will be.
Yes.
KMS. Okay.
That is usually the case with every in Tomita theory, that thing is trivially satisfied for certain group of automorphisms. So that is the modular automorphism group I talked about.
Who consider non-trivial unitary representations first in this case?
Yes, so that's the name selected.
Okay.
Okay, so we are still, so we are in this setup. So we have these Fox spaces, but now we are in the case when Q equal to 0. So we have this free Fox space. So for a moment, we are still considering the free Fox space, but with respect to this twisted Hilbert space. And on this free Fox space, we have this creation operator that we had seen earlier. And some 25 years back, it was defined by Selektenko. The phenomenon is defined just like this. That free ALGEBRAS, and with this he is calling free ALGEBRAS phenomenon. The name actually somehow comes because there are some connection with that, but I am not going to discuss that. So this you can think as free analog of from free probability point of view, free analog of the classical Araki-Woods factors. In some way he explains in his paper, but I am not going to do that. So they are defined precisely by this self-adjoint operator, just like this. And again, your vector varies over the real part.
What's the role of UT in this definition?
What the relation between UT and his creation and annihilation?
So LJ is not defined here. So this HU you are getting is by the twist of So the Hilbert space now you are considering is the twisted Hilbert space. So the twisted Hilbert space.
Everything's the same, and everything is with HU, but now it's.
Now
Only the product.
Inner product is changed.
Yeah.
changed on it.
Okay, thank you.
Yes. So that twist is playing.
Hidden in the scalar product.
Yes. So it is some. So this action is now on HU. That is the important thing. Although this definition does not involve any U.
Okay, cool.
Yes. And the role of U you will see in this fact. So the vacuum vector still induces a normal faithful state. So normality and faithfulness is still okay. But the non-tertiality comes into the picture now. The moment this UT is non-trivial. And this non-tertiality is because of this deformation on this initial Hilbert space. Okay, and the more can be said. The Tinko showed that they are factor and not only a factor where there is this one is non-tertial. He showed that there is no non-tertial state. So he showed that it is of type 3. The moment UT is non-trivial. So type 3 I had mentioned in the beginning, they are not in the 4 categories that you see. And he also showed that they are non-injective factors. Okay, so this was the case when Q equal to 0 and UT non-trivial. Now what we want to do is we want to take Q arbitrary, UT non-trivial. So this is the way I wanted to present the step by step. So here now we have all the data. Any arbitrary Q, any Hilbert space, and any one group of orthogonal transformation. You do the precisely the same steps as before. You first get this deformation HU out of this U, and on HU you perform this Q deformation. Okay. So at each nth level, you have this inner products, and now you have Q Fox space on an U Hilbert space. Okay, so we are doing 2 deformations. The 2 deformations are induced by Q and UT. So Q is making life difficult, and U is changing the things from tertiality to non-tertiality. That's the idea you can keep in mind. And this LQ is as before, and we have seen the formula and for the adjoint as in the past.
Sorry, what is the idea of this twist of the scalar product? Why this combination?
This one?
Yeah, on the right hand side. Why this combination? Twice 1 plus A inverse and this inverse.
So when you take, for example, A to B identity, this is precisely giving the initial.
Yeah, of course, if A is identity, it is the former
So
scalar
although
product.
it's not clear from here, but when I will just talk about modular theory, and many things becomes very nice in that perspective. But I don't know what is the motivation as such, but it is very much compatible with the modular theory that we use.
Is related to this tensor product structure.
Which not really. This definition has nothing to do with this.
It has nothing to do with this
A
tensor power.
priori, it does not have anything to do, but it plays a role in the calculations. Yes.
Can you remind me what this P and Q is?
This one?
Yeah.
Oh, this was the summation over this symmetric
Q symmetrization.
Q symmetrization here.
I just forgot, sorry.
So, PQ.
Okay.
Yes. So
Oh.
we use this
Okay.
strictly positive to define this.
Sure. Thank you. I just forgot.
Yes.
Maybe I think I didn't get thing, this first construction, it was sort of this Q Gaussian von Neumann algebras that work for any real Hilbert space, right?
Yes, any real Hilbert space.
So I don't get where the
But there,
where the
there we-
difference now is, because HU still is some real Hilbert space.
some Hilbert space, yes. But now we are actually having different inner product than the original inner product.
Still some Hilberts. Or do you not complete it to the,
They still complete it.
but then it's still a Hilbert.
So, okay,
Right.
so this HR also sits inside HU. So, okay, the difference between HC and HU is that here the inner product from the original HR is same as the inner product on HC, like induced from that, right? But here the inner product on this and inner product on this are different.
And these two inner products play a role in this.
The two inner
Hierarchy.
product play a role here.
Because they
We're varying it over only HR.
okay. Okay, so that was the thing that I didn't see.
But if you had say a real Hilbert space in HU, and then you vary your Chi over H, that real Hilbert space, then things will be different.
Okay, okay,
So this is important where we vary your vector.
okay, this is strange.
Yeah. Sounds good. Okay, so although it's not like very much clear from these talks, but when you actually do the calculations, then you will see the huge difference, especially things becomes very.
So I have a question. Does this new choice of scalar product makes this A operator bounded?
A? This need not be bounded.
But this expression is bounded, right?
Because A is positive, so 1 plus A inverse is bounded up.
Yeah.
This is from unbounded. Okay,
Yeah.
that's it.
Yeah, but because it is somewhat similar to the construction of the Sobolev space.
Okay. That way.
Yeah.
But the role of this new choice of the norm is to make this operator bounded. So
Okay.
I expected maybe.
But such kind of operators actually appear in the work of ARAKI and WOODS in some. So I think the motivation is taken from.
Mhm.
But again, I cannot give you enough motivation here, so.
Maybe, sorry, is it okay to go back to the definition once again for just a second?
Yes, so I will, so definition is again, I am giving. you-
Yeah, maybe could you just say the star here, is this to which, with respect to which inner product is this?
So here we have both Q and HU. But this is varying over HR only.
And the star,
This adjoint is taken with respect to is in this Hilbert space.
Yeah.
okay,
Yeah. So we have had two deformations and they seem to be hidden, even if this definition seems the same. But the representation now of these operators are changing, and so the Hilbert space are changing. Okay. And
If I fix an orthonormal basis of HR, will this still remain an orthonormal basis in HU? If I form their tensor product, will they still form an orthonormal basis
Yes.
for FQ of HU?
it will.
Okay, so basically in this definition, I can just replace, let C runs through this orthonormal basis. I'll get the same for example.
Yes.
Thanks.
Because it's the this complexification is still a dense subspace. So you take a basis orthonormal basis here, but
Yeah,
it will, well, that won't remain orthonormal. That's the important thing. It will remain a linearly independent set. Which generates the same Hilbert space with the new inner product, but it won't remain an orthonormal set. Because the inner product is changing, they are no longer orthonormal. They're still, because
are they also?
Yeah, but you can take the orthonormal basis for HU.
exactly.
And this orthonormal will be orthonormal in HR.
No,
Why not?
it need not.
Your operator twice 1 plus A inverse. This is self-adjoint. So if you if you are diagonalizing this self-adjoint,
So with respect to, with respect to this inner product,
yeah,
this inner product is not matching with the original inner product of this. So if you have giant,
it's not, but if you have something which is orthonormal to this with respect to this deformed
Mhm.
product, okay, this will be also orthonormal, orthogonal.
no,
No, but not normal.
it won't remain orthogonal, no. In general, it won't. There are examples like, so especially if the,
Even not orthogonal?
no, if the vectors are not fixed by A, then there is an issue.
Yeah.
Ah, yes.
If it is fixed, then okay.
Oh, yes, but you can take. But what are orthonormal bases with respect to this scalar product on the right hand side? It's like taking the orthogonal basis of eigenvectors of this self-adjoint operator, something like this.
I can give you example if in the end of the talk.
But there might not be eigenvectors for A.
Yes, even if they are eigenvector, I will give you an example. So in the end, let me proceed for a moment. I will give you an example in the end. On R square, actually, I can give you. Okay, so here,
Even if there are, there might not be enough eigenvectors.
it's not true. You can imagine, well, can't imagine that I will tell you. But yeah, here is the definition of q-ARAKI-WOODS. So this is the main object of our study for this talk, which is given with any arbitrary 3 data. Okay, and
The representation UT modifies the inner product, Q modifies the tensor powers of this.
yes,
Okay.
yes. So I have listed it here. This is still a non-trivial state as before. But now it is non-trivial when UT is non-trivial. And we will get back to the previous examples for these special cases. So this is the most generalized version, if I have to say. Okay. So let me quickly go through the modular theory. So you remember, so we have 3 data here, HR, UT, and Q, and we have this operator S, delta, and J, if you remember from the Tomita-Takesaki theory. And the formula for this can precisely be given like this. Okay, so there is a precise formula, and A is playing a role here. This A is the analytic generator that you have. Okay, and the way inner product was defined, this formula can very nicely be given in this form. Modular theory is actually very nicely presented. And you will note that there is no Q coming into the picture, even if there is Q here. So modular theory actually does not tell you anything for different.
It does not distinguish, not does distinguish.
Oh, right, sorry. Somewhere it is.
Yeah.
So, thanks. Okay, so here let me also say about the general fact about an orthogonal representation. So suppose you are given one parameter group orthogonal representations. You consider these 2 parts. So you decompose your real Hilbert space as a direct sum of all 5-dimensional sub-representations, and this is the orthogonal complement of this part. So this is called almost periodic part, and this is called weakly mixing part. So almost periodic you can think as they are generated by the eigenvectors, and this is the perpendicular effect. And almost periodic part can further be decomposed like this. So essentially what this is saying that all almost periodic part actually has the as yield source of representations only 1-dimensional or 2-dimensional representations. Okay. And these are precisely up to unitary or up to change of basis your orthogonal representations. Okay. So this is quick review of how a representation on real Hilbert space can be given. And this you keep the name in your mind, almost periodic and weakly mixing, because now when we discuss about the properties of this phenomenal algebras, we can't we usually do it for these 2 different cases differently, and your analysis is very different for these cases. So here is a history behind the factoriality question. So we have seen that in other cases, in previous cases, when q equal to 0 or when ut is trivial, everything is a factor and non-injective. But for this case, it was not so easy to prove today. It took quite some time to get to prove factoriality, and different people have tried it for different particular cases. For example, yeah, so the q equal to 0 case was proved to be factor in every ut. But here I showed that okay, when it is weakly mixing, then it is a factor. He also showed that when it is almost periodic, but the dimension is infinite, then it is factor. Nelson proved a very nice result like this, that for finite dimensional case and q very close to 0, then these actually are isomorphic, irrespective of how ut looks like. It is isomorphic for every q close to 0, and hence because this is a factor, you have this to be factor because of this result. And 17 in 17, two people actually consider the same condition. They found the same result in independent papers. When ut admits a non-zero vector, fixed vector, then you have factoriality. And just last year, factoriality was proved in almost all cases here. So either the dimension is at least 3, or when the dimension is 2, then for certain q, the proved factoriality. So essentially, factoriality was open only in this case. When the dimension is 2 and ut does not have a fixed point from here, and q is in some sense a small. So I'm not going to describe what is small or big means, but you can imagine that it's not proved for all people.
So what happens in this fifth point?
So the fifth point,
Admit a non-zero fixed vector.
yes.
Is it true that if q is sufficiently small, then ut also always admits a non-zero fixed vector?
No.
It's not.
ut is
So it's an independent reason for making it a factor.
Yeah, so you start with ut, which admits, and your starting thing has nothing to do with q.
Okay.
I have a question for the 2015, because it again appears that when q is close, depending on the dimension, then it's a factor. So I wanted to ask whether in here and in the previous cases like that, is there just a close formula depending?
Methods are very close. The methods are almost same in proving the result, but because there everything was tracial for Neumann algebras, things are different. But in this case, when ut is non-trivial, then you don't have a tracial state. So your analysis go through this modular theory and Tomita-Takisaki theory. Although the core idea was the same in proving this, but then a lot of modular theory was there into the proof.
Sorry, how different are these results of Nelson from 15 and Bikram Mukherjee, Ricard Wong from 22?
So here, okay, so here dependence of q is on dimension of HR.
Yes.
Here dependence on q is on the
No, I'm asking about this.
Yes. Sorry, yeah.
Yes, this one.
Here dependence on q is not on dimension, because here for dimension
is fixed, it's only 2, yeah.
Here dependence on of q is
Q
the eigenvector of your
Mhm.
So this away thing I'm not explaining, but this is different than this. Okay.
So the way is different from this close.
Yes.
Yeah, but
It's not just opposite.
But how much different are these? What was the meaning of this clause?
I'm not going to explain that. It will take some time.
It's censored.
You can check that. So it in some sense it is inversely proportional to the dimension. You can.
Okay, at least in dimension 2, what does it mean to be close to 0?
Q is close to 0.
When the dimension of HR is equal to 2,
Then Q will be like very.
how small the absolute value
There is
should be?
some number depending on dimension.
And you don't remember this number.
It's like there is some formula, a function of Q. Like I don't have to give you. You can check the book. So the formula is not like Q square or something like that. The formula is a bit a polynomial of Q, something like that. So I don't remember exactly the formula, but you can check the paper. Yes. But there is certain Q for which it is proved. So the proof itself like is not for every Q, and Q is given for us like the formula for that, how close or the polynomial in Q is not so like 1 degree polynomial. It depends on.
Yeah,
the
but
degree.
I was asking about the relationship between the dimension of H R and this condition of being close. Because it depends on the dimension. So I was asking what is happening if the dimension is equal to 2.
Yeah, so there is a formula which I don't
In
remember.
this case, this
I mean, you
formula
have
for
to,
this
but
bound is
Sure.
very complicated.
well, I mean, formula is always very complicated, but you plug in the number 2 and you have an answer, right?
And
So the short answer is I
By no
don't
means.
remember the formula.
okay, so it's substituting 2 doesn't simplify.
No, it does not. It simplifies, but not for all Q. It works only for certain Q. And for all Q, okay, so this is what we have proved. So we completed this for every Hilbert space. So in this case, so our result actually works for any finite dimension. Our method works for any finite dimension. So I have written it for that case. So you have these 3 data, and then it is always a factor. We also at the same time showed that it is non-injective. So earlier people had tried non-injectivity. There were 2 papers. We proved it in general that they are non-injective. So far we have proved the result as before for other cases that they are factor and they are non-injective. And moreover, it is of type 3. So I am not going to discuss the type in the upcoming slides, but I have just mentioned that they are of type 3 at the moment it is non-trivial. And although
Is this a unified proof using the same method to cover all the previous cases?
no,
No.
our method are very different.
I mean,
These new methods do not apply to previous cases, right?
but no, I mean, does this result depend on the previous results somehow? No. Oh,
This result is independent of the, so if the previous result, yeah, so the method itself is very different.
so indeed, this gives a unified proof of the known cases in the case. Yeah.
This actually gives the unified proof in every general case. So you can get all the previous result using this, even in infinite dimensional, by using some method, some abstract method. Even, so you can avoid the previous result altogether, even for infinite dimensional case. So that's what I have written it here. At least for non-injectivity, you can avoid all the previous methods. Even factoriality, you can avoid.
Yeah, that's very interesting.
Yes.
That's why I'm asking. Okay,
So at least I should mention that at least you can avoid all the cases except this one. So for almost periodic part, you can avoid all the cases, or all these things, but you may have to still use this fact for the
So your result gives non-injectivity,
non-injectivity and
but
fact.
not being a factor.
So the third point.
That's a factor, look,
But yeah,
most important
yes,
thing.
okay.
And also the third point is also not covered right in the previous slide.
Non-injectivity?
No, the previous slide in a case where dimension is infinite, the factor should be non-injective.
Yeah, it was not covered.
Okay.
No. And non-injectivity was proved only for weakly mixing case.
Okay.
And it was for finite dimensional case, it was not proved earlier at all. In fact, there are some results which I have not mentioned, but in some other cases it was.
But it is expected that all these 3 conclusions should still hold true for the infinite dimensional case.
You can conclude from these 3. So you can use some inductive limit argument to conclude about the infinite case. So you reduce your infinite dimensional problem to finite dimensional problem.
Okay.
And then you use this. That's the idea. At least in almost periodic case, you can do that.
I mean, for example, if the dimension is infinite, is it still true that this is a factor?
Yes, so we have already seen that for dimension, I already said that. This case covers almost.
Yes, okay.
Okay.
So it was
This
known.
is the source of this being a factor from this. You are taking this from this
Yes.
for infinite dimension. Okay.
Although the unknown case was only this, our result actually gives all these previous result as well. But it was known, yes. Okay. And same, you can conclude non-injectivity for all the cases. So, so this is our result, and I have, well, 10 minutes, so I think I won't talk about the proof. I won't have time. So, well, I will simply say that there are a bunch of methods of something called conjugate variables, and that was not used previously. And all I want to say is that so there is an abstract result of Brent Nelson. So this result is for general von Neumann algebra, which has some conditions. So the condition is M is generated by a finite number of sets consisting of eigen operators. So there are a bunch of adjectives which admits some property. And then you can immediately conclude that it is a non-injective factor. So our method was simply to find such set G which satisfies this condition. And then you can say that it is non-injective. So
Could you explain what is an eigen operator?
I am not, it's written here, but
Here.
for the lack of time being, I'm not going to explain.
Consider what is called an eigen operator.
So I have not explained anything. I did not explain you what conjugate variable is or what I can. But I am just for quickly saying you that okay, you can use it like this. So the main idea is this, that we want to apply this concretely for this. And so we want to find such set G, and we have found such set G, and we satisfy this condition. So that's the main idea behind the proof. But
What are these AIs?
AI are some operators like generated. So there are some bunch of operators.
But wait a minute. So,
Okay, I see it now, sorry.
but now EI,
the obvious choice.
Yes.
EI is complex now.
Yes, yes. So that's why there is a bar here.
Yeah.
So in the formula, when you take complex numbers, you have to put a bar here. Anyway, you forget about this. This is just for the mention that this is how one can approach these problems.
So this orthonormal basis is actually in each U.
Yes, yes.
Okay. Right.
Okay. So there is this method, and our method was inspired from a very recent paper of Miyagawa and Spiker. So they actually did this fact. They proved it for the case when UT is trivial, and actually we just took their ideas and we proved it for non-trivial case. And there is some notion called conjugate variables. That is exactly what we have to.
What is this conjugate variable?
I am not going to explain that because you already took me a lot of time. So that's the idea behind this. Okay. And then in remaining 7 minutes, I would like to talk about these two notions, solidity and fullness. So let me just say that, okay, now we know that they are non-injective factors. And we know that, okay, when you study injective factors, so then we have already a classification of injective factors by the work of Alan Kohns from the 70s and 80s. So now the next step in like the big research in von Neumann algebra is to understand non-injective factors and classify them. So in order to understand non-injective factors, we want to understand some properties because classifying them is not so obvious and easy.
Sorry, correct me if I'm wrong, but xi times x minus xi times x.
It should be x times xi.
Okay.
This should be commutative.
Yes, yes.
I mean, 0 tends to 0, just a constant.
Sorry.
Okay, so I have two typos to correct for the slides.
So this is like an asymptotic center.
Exactly. So I was saying that in order to understand non-injective factors, these are some of the properties like solidity and fullness that we want to understand or study.
So asymptotic center is consists of asymptotic components.
Exactly. So the fullness is somewhat a stronger version of, as you said, of factoriality.
Nicely put, yes.
So full simply means that if something tends to 0 in like commutes in the limit, then it has to be scalar in the limit. That's the idea. So instead of so factoriality is about that. Okay, if it commutes, then it has to be scalar. But here everything is in the limit.
So it's a more stable kind of factor of being a factor.
Yes, you can say that.
I'm confused about the date. So this result of Alan Kohn comes from the future, 2007.
So Alan Kohn defined it differently. So his main definition of fullness was different. And Marakchi gave this formulation very recently. So the original definition is different, which I didn't want to, because this looks very nice. You can compare it with factoriality, but the original definition uses something else. That's why this is from the past version.
Only 100.
And this notion of solidity was defined by Ojawa for type 2 case, and Houdet and Round they define it for type 3 case. So a phenomenon algebra is called solid if the moment you have a subalgebra inside M with an expectation. So there is a conditional expectation from M to N, and such that the relative commutant is diffuse. So the relative commutant means that every element in M which commutes with N, and diffuse means that there is no minimal projection.
So what is the
No minimal projection.
no minimal projection? Okay.
Then in this case, N must be injective. So the definition is not very inspiring at first, but these are some of the notions that you study because
Could you explain what happens if M is equal to B of H?
then it is always solid. Any injective factor is always solid. And our result actually proves that at least for the dimension infinite, it is solid. And these are the questions that you look as for this non-injective. So I have 4 minutes. So in the 4 minutes, I just want to say that we have actually more results about fullness. So for a moment, I want to emphasize on fullness. And there has been a lot of research also on how to prove fullness. And here is a historical background. So when UT is trivial, then different people have proved fullness for different cases, just like factoriality. When UT is non-trivial, then these people have proved fullness in many cases. And here I want to say that the remaining case for fullness was when the dimension is infinite. So this is not like factoriality. So here, if you saw earlier, the remaining case for factoriality was when the dimension is 2.
Now it's
But here,
infinite.
if dimension is infinite, UT is almost periodic, and this is the spectrum of your analytic generator area.
Okay.
This is unbounded. So then,
Is unboundedness of the spectrum of A equivalent to unboundedness of
Yes.
the generator H?
yes.
Yes. By functional calculus.
So why not writing H unbounded?
Because I want to because the proof and everything actually goes through the eigenvalues, which tends to 0. So I wanted to write it in this. Well, at least here it's not obvious, but it is there. So the only remaining case was solved. So this is with Siemens, where we proved that in the remaining case it's full. And okay, so this was the remaining case. So the corollary says that it is full all the time.
Great.
Okay. So this has still not appeared. Hopefully, probably we'll see it by the next month. And here's the summary. In last 2 minutes, I can say that okay, what we proved. So we had 3 data. We constructed this q-ARAKI-WOODS phenomenon algebra in general. We discussed factoriality, non-injectivity, and fullness. In particular, we proved that it is a non-injective factor for every case. It is of type 3. For non-trivial UT, it is solid at least when the dimension is finite, and it is full all the time. So this is the cases that we have covered. And what more we would like to know? So we would like to know that it is solid in all the cases. That's the first question that one can ask. And I have written something about Cartan subalgebra. So you may have seen this notion somewhere for CS that these are subalgebras whose normalizers generate your phenomenon algebras. So in CS algebra, you will see that the normalizers of your subalgebra generate your CS algebra. So these are notions we have come across.
So what about the existence of the Cartan subalgebra for this L of free group?
Yes, I was coming to that. So let me just mention these questions. So we want to, I will come to your question. So we want to know that whether the lag patterns are available. And I'm already using lag because we have some information for the other cases. So whether there is cartons available or not, and whether it is strongly solid. So this term strongly solid is a stronger version of solidity. So I'm not going to define what it means, but what all I can say that strong solidity implies both these two cases. So strong solid. So if we can prove that it is strongly solid, then these two questions will be solved. But a strong solidity is not known for any cases.
But it's just strongly solid that allows with implication. Solid does not imply.
No, solid. So yeah, these two conditions are somewhat not independent, but are not so much related. But this one is. And another question that we can ask that, okay, so I have defined this for Neumann algebra for the deformations coming from Q. But some of these deformations actually, you can give it for even a non-real Q. So there are some definitions, okay? But in those cases, you have to say that, okay, this PQ and that we have defined, they have to be strictly positive. So you assume in those cases that they are strictly positive, and then you can define everything. And in those cases, you would like to know that whether all the properties that I have presented, whether this property is satisfied.
So that's what I mean by other, that's when Q is not real.
Yes. So other deformed phenomena, whether they satisfy the property. And this red line says that all these three properties are known in these cases. So in particular, your question says that for free group factors, all these three properties. Okay. Or when ut is trivial. So ut is trivial is the case when free group factor Q equal to 0, and even if ut is non-trivial, then it is known. So even in type 3 case, we have some result. All this. So these are some of the questions that you are invited to look into. So I am.
Thank you so much. All right, any further questions? Maybe we start from the room. No? Anybody from?
I have a question.
Okay, go ahead.
If you have this family,
Mhm.
when Q goes between -1 and 1, do you have this continuous field of factors, something like this? Can you organize this deformation in some global object, like so? In sister algebras, you have the notion of a continuous field of sister algebras. What is happening here?
You change your
Normal algebras.
you change your Q there.
Yeah,
Yes.
yeah.
Yes.
Uh-huh.
Do you have an
Nice question.
analog of?
Yeah, nice question.
Is it some kind of measurable family?
Yeah, I like that question.
I'm not sure I have seen this anybody doing that, but
Because
I guess
strange phenomena happen from the point of view of this previous result.
Right.
Too small.
Okay.
So in different parts of this family, different things happen.
Yeah,
So there you consider topology to be the usual topology R?
Maybe not topology, maybe it's
Measure.
kind
Measure you consider.
measurable family.
Borel structure maybe.
Yes, yes, something like this.
No, but in C-star algebra, you still consider Borel structure, not the continuous.
no, for sister algebras, we have this continuous field of sister algebras, right? And it's typically, at least, I think, that what you've got, that you just have two cases, Q equal 1 when things degenerate, and Q different from 1 when things are all isomorphic.
Okay.
Yeah, I don't know, take the sister algebra of SQ2, right? I mean, it's
Right.
isomorphic for all Qs except for Q equal to 1.
Maybe not necessarily typical.
Maybe I should say typical, but
There are
typical might
known
give some-
examples.
Yeah.
It happens.
Yeah, it's not infrequent that it happens, that these fibers for Q, which is not 1, are isomorphic.
But here, much more interesting
Kind of-
phenomena.
-1 is not much.
Yeah, okay. I mean, generic for Q.
Yeah.
These kind of questions are actually like very well open in this regard.
That's why so many of these formations are graph sister algebras, because Q is developed. Because the
Right.
So definitely in this Sitter algebraic case, you have some mild behavior outside this limit point, and in this limit point you have some jump. Okay.
Yeah.
Here you have quite complicated structure. Many things can happen.
It's
Depending
all
on
to be, yeah.
And even here, if you just consider the C star generated by these Gaussian operators, even then in this case, I think whatever you are saying, for different Q, we don't know anything. So instead of generating the von Neumann algebra, you just take the non-closure. And you asked all the questions, whether they are simple, whether they are non-injective, how much they depend on Q and everything, and nothing is known. So the C star algebra itself is a big issue. So at least in this setting, whatever you are saying, it's not close, even not clear even for C star.
Yeah.
What happens for these Q Gaussians if Q is greater than 1 or smaller than -1? Does this possible?
So
Or do we get something unbounded then?
you can define it, but I don't think you will get bounded operators in those cases. So these left creation operators won't be bounded, I think. So the things will become very, even for Q equal to 1, it's not like the analysis is very different. So.
Yeah, well, I was hoping that maybe like the norm of this Gaussian operators is maybe some analytic function that has a pole at Q correspondent, then you afterwards you could maybe continue it.
Not sure. In quantum groups, there's sometimes if you replace Q with Q inverse, you will get isomorphic objects. I'm not sure if we
Probably
the same.
referring to this phenomenon.
Yeah.
Yeah, yes.
If so, then you won't get something new. If so, but I'm not sure if this is the situation.
No, so for Q inverse, this inner product that we have defined will not be an inner product.
Yeah. But you can do it in some other way.
Yeah, if you propose some other way, that will be then this won't be. Then you have to say that okay, for Q less or equal to 1, you are in this
Different
set.
form.
Yeah, so you have to verify like.
I mean, I assume
This
defining what the relations of this star algebras that might work for, they might be, maybe could realize them. Or
For example, if the absolute
Relation
value of Q is larger than 1, you replace Q with Q inverse.
then what is the change? You're not.
Yeah.
Formal.
So yeah, in this case, if you want everything to make sense,
Then all the results.
the object corresponds to
Replaced by 1 by Q.
Yeah, in this case, in order to make everything make sense, the object corresponding to Q is isomorphic to the one corresponding to Q inverse.
I don't think each question is.
Not sure.
that would be
Because you are
the answer.
not defining anything different.
Yeah, exactly.
But I guess in SEQ2, there you are probably defining.
Wait.
Saying that.
Which is one of my next questions. How do I know these von Neumann algebras are pairwise isomorphic or non-isomorphic? There's some result because I remember you mentioned sometimes.
For some result.
Yeah.
I told you those 2 results.
Yeah.
And that's the only thing.
Yeah.
And
We don't even know by varying these Q and these representations, we can get a continuum of non-isomorphic von Neumann algebras.
There are some results. You can. So for.
Are there infinitely many of them?
Yes, they are uncountable.
Okay, great. I have another question is, are people studying other kind of approximation properties of such von Neumann algebras, like the Hagelgroup property?
So Hagelgroup property, complete metric approximation property.
Yeah, something like
Both
that.
are known to be true.
Okay.
They are worked by Matthews.
Okay.
I cannot say about that, but yes, approximation properties are relatively easier to. Well, not easier, I should say, but they are like the results are known. They were known even before the factoriality.
Oh, okay.
Anybody else? On Zoom, we have only Ian. Ian, if you want to ask a question, it's your last chance. Okay. So in this case, let me ask you a little bit, philosophical question. So please correct me if I'm wrong. Your story is about constructing von Neumann algebras of factors, to be more precise, from Fock spaces.
Yes.
Okay. And how subjective this procedure is? I mean, can you point to me some nasty factors saying this will never come from any Fock space by any construction? Or is it more like you can get basically almost any factors you want? Imagine that you reverse engineer, but I have a given factor and I want to construct it from a Fock space.
So, okay. So there are not much result in this regard, but there are some results. For example, there is a result by Houdier and I think Eric Ricard. They showed that these free group factors, free ALGEBRAS factors, they are not isomorphic to some of the phenomena which was constructed by Alan Kohns in 70s. So those phenomena were constructed by Alan Kohns were some of the very they were the mainly known type 3 factors at that time. And over the years, many other fundamental algebras were also constructed. But at least among those constructed in 70s and 80s, some of them are not known to be isomorphic to these free ALGEBRAS case. But for the Q non-zero, we still don't find. There has not been any study.
Because for instance, in sister algebras, when you talk about the celebrated Jiang-Shu sister algebra, which has its own definition, we know how it is constructed, and it's a very, very mysterious and beautiful sister algebra. All of a sudden, bang, people write some paper about foliations on S3, some broken orbit construction, and by classification, they prove, hey, this is exactly Jiang-Shu sister algebra.
Yes. So such things are here as well, because there have been some construction again from the 90s, and very recently some people showed that okay, that construction is isomorphic.
Perfect. This is so.
Yeah.
Okay.
There have been such.
Okay. This answers my question. So let's thank the speaker again. Thank you so much. Odin.